So this next presentation is I/O transformations. So we're going a little step further from the generalities of the last presentation and talking a little bit about what happens in the storage stack to account for these storage systems. So we know there's a lot of hard drives, there's a lot of servers, there's a big network. How does your file get mapped onto that? So if you take this illustration, we'll pick a file. Say you're writing a large checkpoint file in HDF5 format. If it's a big file, what you want to have happen ideally is that it will be split and divided up across those servers so that when you're accessing that one large file, you're not constrained to just the performance of one server and its hard drives. You want it to get the performance of all the servers simultaneously. So we call this striping. This is dividing up the file into chunks or blocks, divvying those blocks up across all the servers that are available. And then each server has a collection of disks that it will further subdivide the file onto so that, in the perfect world, you have a big file, it hits all the servers, it hits all the disks, you just get lots and lots of performance. So the optimizations are all about kind of making good use of this striping and how we get these parallel paths to your hard drives. So how does this striping happen? What are the exact policies? So on Mira, this is kind of an automatic thing. You can't control it even if you really want to. The bigger your file is, the more servers it's going to take, the more disks it's going to take. That's kind of how it works. On the Cray systems, Theta and Cori, if you don't tell it any better, it's going to take every file and put it on exactly one server. This is good if you're making lots of files because each file will get its own dedicated server that it's going to reside on. If you have one big data set, that's not great because you're not taking advantage of all these other servers that are out there. So this is a tunable. It's just they have to pick one way or the other as the default. So you need to be aware of that. It may be a good default for you, it may not. So there's you can put in your job script an option that will say, for this directory, I want file striped differently. There's actually an example in the hands-on scripts for Darshan. We'll talk about those a little later, but if you want to see firsthand what this might look like. On the Argonne system, you can use this command, lfs set stripe. -C is kind of how many servers you want to stripe across. -1 says all of them, however many there are. And you can set this parameter on a directory, and then every file you create in that directory will be striped across all the servers there are. At NERSC, they have commands like this. They're kind of wrapped in a little user-friendly command tool. There's, I forget, set stripe medium or something like that, but that's documented on their website. And it gives you some rules of thumb. How big is your file? Maybe you should do this setting to kind of guide you a little bit. Now, assuming you have a file that's been striped across many servers, what does that mean for accessing it? Especially if you're accessing it in parallel. Obviously, we're writing parallel applications here. You can think of it as a global shared memory region that anyone can access. And that means that these chunks of the file that are divided across servers have locks to protect them because multiple people may access part of a file at the same time. You don't want to get garbled results. So it has protections in there for that. What happens when when one of your processes accesses a file is it acquires a lock before doing the I/O. It starts doing I/O. There's some good things about locking. This can be problematic for performance, but it also means that while a client has a lock on a part of a file, it has full control over it. It can cache the data, that sort of thing. When someone else wants to access an overlapping part of the file, they have to fight a little bit and coordinate on who has the lock. So what does that mean in terms of your data layout? We've got 3 examples of how data might be distributed within a file. So one option is that you have kind of chunks of data that are big, multiple megabytes. They're perfectly aligned with the layout in the file system. And so what happens is when the green client accesses its data, it gets a lock. Yellow client gets a lock. Purple client gets a lock. They're not conflicting with each other. They can go completely in parallel, no coordination, access their parts of the file. There's not much overhead. That works great. Now imagine your data is divided up a little more fine-grained, or it just doesn't magically line up with the boundaries. Then you're going to have some overlaps. So there's a block right here that is shared by the green client and the yellow client. That means they can't do I/O at the same time. One of them is going to get the lock, do its I/O. The other one's going to get the lock, do its I/O. That means it's slower because you have a lot of hard drives available, but you're taking turns using them. And then, going even a little further, what if you have an even more sophisticated data model and you're kind of jumping through a multi-dimensional array and it doesn't really have much of anything to do with the layout? It can get worse than that. You can have a lot of contention on block boundaries and kind of even little small pieces of a block. So this locking is something that we think about a lot in optimization and what the data libraries do. So one example of how to combat this is to have some transformations in your storage stack that can take an access pattern that your application described and convert it into something that's friendly to the file system and the storage system. And usually the objectives are sometimes you need to simply reduce how many operations are getting to the file system. We've got way more compute nodes than we have hard drives. Maybe it's too many things to just have them all really get there at once. We want to avoid the lock contention that I talked about on the last slides, so that we can get more activity at the same time. And just simply, sometimes the software isn't totally happy with that many entities interacting with it, so we kind of funnel things down. So the most important transformations and what you'll see most common are what we call transparent transformations, which means whatever the application does gets translated into the file as if it had been done explicitly verbatim the way you said it should be done. The end result matches what you expected. Some magic happened in between, but the net result is indistinguishable from you doing the operations in sort of a straightforward way. So we're going to kind of go through a few examples. These are things that will happen automatically in HDF5, Parallel Net CDF, Adios, and MPI-IO. If you find that you are hand coding some of the things that I'm talking about here, maybe you have to. Every application is different. But if you find yourself spending a lot of time working on that, it's worth the time to kind of look around and see if there might be a off-the-shelf solution that could save you some time. So, the first example I'll talk about is data sieving. So, I mentioned earlier that the latency to these storage systems isn't great. It does better at big transfers. So one thing that may happen, suppose you have an application that has a lot of little pieces of memory that it wants to populate from a file. And you can do this both in the read step or the write step. This is actually a write example. So one way that you could do this is issue a separate write for each of these pieces in the file. So, one write, the next write, the next write, the next write. Maybe you're issuing them concurrently if you can. But what that looks like to the file system is it has a lot of small operations hitting it. Some of them aren't aligned. Some of them are going to have lock conflicts. It's not great. So data sieving is kind of a little bit of a non-intuitive optimization, but what happens in data sieving is the storage software reads in the entire file into memory, so one giant read, and then with the data in memory, makes updates to it, and then writes the whole thing back. So what this does is, instead of the file system seeing a ton of small operations with little gaps in between them, it just sees one big read, it knows how to do that great. It sees one big write, it can do that great. And there's a lot of scenarios where that's actually significantly faster, even though you're moving way more data because you're avoiding these small operations that just aren't good for the file system. And so that's one example of something that can be done to avoid contention. Another one we heard in the question earlier is two-phase I/O. So two-phase I/O is similarly trying to organize data. It doesn't do extra I/O than what you asked for, but what will happen is, again, suppose you have little pieces of data that you're trying to write. Maybe they're interleaved across processes, so you're accessing data in the file according to what your simulation needs, not according to what's kind of pretty for the hard drives. And so sometimes instead of writing these interleaved pieces, the fastest way to do that is to select a subset of processes that are going to be your delegates, the people that are going to really access the file system. You do a shuffle phase that hands the data to those, we call them aggregators, the delegates that will kind of combine these into big chunks. And then those aggregators will then write them to the servers. And what this does is we'll get to this a little more on the next slide. There's a few things that happen here. One thing that happens is that you can, even though you have these little pieces, maybe it's not balanced, two-phase I/O can balance the data across all the processes that are accessing the file system so that they're all kind of using nice big chunks. The second thing they can do is that they can write these chunks in block-aligned units so that you don't have any lock contention at all. They're all perfectly lined up with the blocks on the file system. They're perfectly aligned with lock boundaries. Things go faster. And then not only that, they can be divided up according to servers so that you're issuing operations to a particular server from each of your aggregators. And then finally, it gets even more crazy than that on our more recent machines, is that the aggregators might be chosen because they're close to the storage system. The network fabric's complicated. There's toruses, trees, fat tree networks in the way. And the software can figure out which of these nodes can talk to the server you need to talk to the quickest, and they can pick those. So this is a set of, a stack of 4 things that are making your I/O go faster that two-phase I/O can do for you. And that kind of hit home why, what the impact can be. We'll take an example of a particular simulation code. This, a big application that's been running on our systems for years called S3D. And S3D has, its data model is interesting to look at. There's multi-dimensional arrays. There's multiple of them, and they're not all the same dimensions. There's some 4-dimensional arrays, some 3-dimensional arrays. It tends to access data in subarray patterns. And it's kind of complicated to draw a picture of, but this is a pretty good cut at it. So what happens when you try to write data that's in this format? It's kind of distributed in a way that's great for computation. This doesn't look so good for the storage system. So we looked at this. We did some instrumentation of S3D and tried writing the data with different mechanisms to see what the outcome was. And I'm showing 3 cases here. One is kind of the default, what you would get if you didn't use any optimizations. The second one turns on data sieving, and the third one does collective buffering. And the important thing is that the application didn't really change in any of these cases. This is just a very small example, 16 processes. They're doing 64 writes. They're complicated writes with a data pattern that they're trying to do. But application's doing the same thing, and we're just toggling flags that turn these optimizations on and off. If you run it with no optimizations, you turn off everything there is. You're not writing much data. It's just 6 megabytes for this small example, but it takes forever. It takes over 1,000 seconds to write 6 megabytes. So not good. And in fact, the runtime is only tens of seconds longer than the I/O time. So you spent almost your entire core hour budget trying to write that 6 megabytes of data. If you turn on data sieving, we drop that down a lot, all the way down to 11 seconds for the runtime and 4 seconds for doing the I/O. The interesting thing, if you remember I talked about data sieving, you may read in some data, modify it, then write it back out, and you'll move more data than you need to. So in this case, we moved 87 megabytes instead of 6 megabytes, so it's tremendously more data than you meant to access, but it's way faster because it's organized much better. And then finally, in this case, with collective buffering turned on, that dramatically reduced it again. We're all the way down to 0.6 seconds is the time we took to do the I/O. The runtime is now 6 seconds. So we've gone a long ways just by using an optimization that's suited for this particular complicated data model. So this is why this is important. If you have a code that's doing something like this, if you kind of don't use the right tools, you're going to be in some trouble. Another type of transformation we can do is on these I/O forwarding nodes. These are the nodes that talk to the file system, and they kind of act as a bridge between your compute nodes and the storage system. And they do a few different things. So Mira is our older machine that we're a little more familiar with, but it bridges 2 different kinds of networks. There's the network that your compute nodes get to use to talk to each other. There's the network that the storage system uses, and something has to bridge those 2. It runs the file system software and understands how to talk to GPFS. And they funnel down the operations from a large number of clients to a smaller number of clients. So when, let's say you're a GPFS server and you're looking at what's coming in, you only see a few hundred people trying to talk to you instead of nearly 1 million people trying to talk to you at once. And it can do a few transformations along the way to make this even nicer. On Theta, it doesn't have I/O forwarding nodes per se. Well, it does for some cases, but the primary file system uses something called a Nelnet router instead that looks very similar in terms of a diagram, but it's mainly to bridge networks and kind of shape traffic and direct it to the right place in the storage system. So the kind of transformations you can do here, you could imagine that you have 100 processes that all open a file. If they go to the same forwarder, that forwarder can do one open. So it can reduce the number of operations that are getting to your file system. It can merge, kind of do coalescing of large accesses into, or small accesses into bigger ones. You could have a cache there. These forwarders or routers are in a position to see 2 types of networks and can make optimizations that require knowledge of both. So it can pick a path through your InfiniBand network that will get you to the storage quicker. And these are things that are usually provided by the vendor. So that's part of the throughput of the storage system is assuming that these things are going on. And sort of the last flavor of transformation to talk about are the not so transparent ones. So what I mean by that is you could access a data set and have it be converted into something totally different on the storage system by the time it gets there. So one observation, if your processes are writing to separate files, there won't be lock contention because each file has its own locks. So one thing you could do is access a data set from your application. It looks like one big data set, but then the libraries up underneath could split it into separate files in a nice way. So if you do that, you need to stick to the library that you're using because the underlying files might not make sense by themselves without the translation layer that knows how to put them together. And the software does that for you. The library can do that for you. And then, not necessarily just splitting into different files. In the future, we might expect that this could land data on different types of storage entirely. So this is kind of moving to a model where you don't expect files as kind of your baseline thing. There may be some other layer on top of it that makes it look like a file and understands this is being mapped to different devices. And just to give some quick examples, the Parallel Net CDF library has a feature you can turn on called Subfiling. So when you access a Parallel Net CDF data set, it can split it into files in a way that kind of makes sense for your storage system. Most likely that's somewhere between the extreme of one big file and the other extreme of a separate file for every process. Neither one of those is optimal on some systems, so it does kind of the Goldilocks, maybe you need 5 files, maybe you need 10. HDF has its own sort of layer within the library called the vol interface, and that can be used to connect HDF5 to all sorts of things. It could connect to a web service even. So that's an example of something that can translate a data format that you're familiar with into a different storage target entirely. And a little bit about the file per process issue. Why not just do that? So you could forget all this and just say each process is going to open its own file, do its own I/O. For some applications, that's easy. For some applications, it's not. From a performance perspective, will it perform well? Honestly, it does a lot of times. Particularly at smaller scale, particularly on the Lustre file systems are a little better at this. What we see if we kind of survey across the users on our systems is that for relatively modest jobs, this happens to be from Intrepid, this is a little bit old data, but for modest sized jobs, that's pretty common strategy. It's gets you some good results, maybe the I/O is fast. But as jobs get larger and larger, it sort of becomes intractable at some point. If you're running something that has 100,000 processes, maybe just for management reasons, you don't want 100,000 files. That's going to be hard to deal with after the fact. So either because it's hard to manage or because there's sort of a crossover point in what the best strategy is, we see a lot more kind of shared file use on the bigger applications. So just to kind of recap here a little bit. So if you look at kind of the history of kind of high performance computing and network computing, that we usually expect that there's a file system, looks like a normal file system, and your file system manages it. It tells you where the data is going to live. But since then we've kind of built up this infrastructure of pieces that can help you use it more effectively, and we have transparent transformations that kind of work within the limitations of the file system and organize data for you. Particularly the things like NetCDF and HDF that have a way to express what's actually in your data, how many variables there are and what their dimensions are. That means they have a lot of information about what you might be doing with those variables and kind of can take that into account when they're laying it out. And they keep the portability, so you can take a NetCDF file that was written 10 years ago and it's still pretty easy to open it up and see what's in there. And we know the storage systems are going to change, and we may have some different things under the covers later. I think we'll get into some more specifics as the day goes on, but I just kind of wanted to give you a feel for what things are happening here and why they're so important and how they might benefit you. I think we're going to turn it over to Rob next, but before I do that, does anyone have any questions about the material we just went through? Sure.
So do you feel like these supercomputer file systems will move more towards like file systems like ZFS that worry about data integrity, or something like ButterFS?
Yes, well, so that's a complicated question, but the reality is what happens behind most of these file systems is already in that direction. If you look under what's under the Lustre file system on Theta, it's not ZFS, but has something with similar properties for this particular use case called, I think it's Grid RAID that's running on there, but it does striping, it does some integrity checks. But I think a little more forward-looking, what we expect is that storage is going to get a little more stratified, so maybe you have a bottom tier that really has these checks in it and has this redundancy, and then maybe you have a layer on top of it that doesn't have all that stuff but it's real fast. And so it's going to be all about managing your fast layer versus your kind of campaign storage that can do that stuff. So I think that's what we'll see more of in the future.